I think we can all agree that we want our sequences to converge faster, and we would do pretty much anything to actually get that. So as a result, let's talk about the acceleration of convergence. How can we actually get our sequences to converge faster? So let's suppose that we have our sequence xn with n going from 0 to infinity, and it converges to some value L. So let's imagine that this is a linearly convergent sequence. What we're going to consider first is something called Aitken's delta squared process. So this is actually worth writing. Aitken's delta squared. And the idea here is as follows. Essentially, we formulate a new process that supposedly converges faster. So we're going to have a new sequence which is going to be x star n, with once again n going from 0 to infinity. And x star n here is defined as follows. We define it as x n plus 2 minus the following fraction. So at the top we have x n plus 2 minus x n plus 1 squared, and at the bottom we have x n plus 2 minus 2xn plus 1 plus xn. So we now have a new process to consider. So let's take a look at an example. So let's suppose that we have a sequence where xn is equal to the cosine of 2 over n plus 1. Now this sequence converges linearly to a value of 2. So let's try to determine the first 5 terms, for example, of the sequence given by the delta squared process. And in order to do this, in order to determine a particular x star n term, because that's what we're actually after, we need to have the terms xn, xn plus 1, and xn plus 2 as well. So we actually have to determine the first 7 if we're interested in the first 5 terms of x star. We need to determine a whole 7 terms of xn. So let me briefly plot the actual values here. Okay, so just from looking at this, you can see that x star n certainly appears to be converging faster to the value of 2 than xn, and that's actually what we wanted. Now what we can do is we can apply a modification of Aitken's delta squared to a linear convergent sequence that's obtained from a fixed point iteration, and we can accelerate the convergence to quadratic, and this procedure is known as Stephenson's method. So Stephenson's method is somewhat different from Aitken's delta squared because to find a solution to some equation in the form x equals f of x, for example, given some initial estimate x of 0, we compute the following. So we compute x1 as f of x0, and we compute x2 as f of x1, and then for each subsequent term we compute xi plus 3 as xi minus, and here we have xi plus 1 minus xi squared divided by xi plus 2 minus 2 xi plus 1 and plus xi. Alright, so without Aitken's delta squared process, Stephenson's process looks like this. So to find a solution of f of x equals 0, for example, you start by choosing some point xi as the first estimate, and then the subsequent estimates are computed by the following formula. So the subsequent estimate xi plus 1 is equal to xi minus, and then on top we have f of xi squared divided by f of xi plus f of xi, like this, minus f of xi. So let's actually take a look at how this is done in MATLAB. Okay, so here is a definition of Stephenson's root, and what we're doing is we're essentially trying through 100 iterations, and you can certainly change this number, and we're trying to get the appropriate result and looking at some tolerance. So we have a tolerance value for the kind of error that we might actually get. So let's take a look at how this would actually work. Let's do format long, and then I'm going to define a function f, a function of x, being x minus 2 times e to the minus x, for example. And now let's suppose that I want to find the root of this function. So that would be Stephenson root with passing in the function itself as well as the initial guess, let's say a value of 1, and here is the final result.